In this lecture, we're going to look at some of the tools for representing signals that appear to be random or have a high degree of uncertainty. So real signals often appear to have random or unpredictable or uncertain behavior. Here's two examples. On the left, we have a section of sound that is from the letter S in saying the word 6. And if you think about what happens when you say an S, the sound is mainly formed by the turbulent airflow around your tongue and teeth and your mouth. So we would expect that due to that turbulence, the fluctuations in the signal would be somewhat uncertain or difficult to predict in advance. Now the vowel I in 6, here's a short section of that, we see has a little bit more predictability to it. You can see that it's almost a repeat from here, this section, over to here, and over to here, and there's some of the same features as we move some distance away, but there's still a lot of uncertainty about this signal. It doesn't repeat exactly, and it's hard to predict based on what I observe in one interval, what might happen in another interval. Now, the sound I is formed by a resonance in your vocal tract, and because it has a resonant behavior, the characteristics are a bit more predictable, less uncertain. So these kind of signals where we have these aspects that are not known exactly ahead of time are quite frequent in signal processing. And what we're going to do is use the tools of probability and statistics to model this uncertainty in a principled manner. And by modeling the uncertainty in these signals, we can actually use different properties to separate signals from noise. So statistical signal processing is a very powerful approach for dealing with uncertainty in signals. Now the way we're going to think about this is as if I have a big bin or a big container that is full of different signals. And when I actually perform a measurement, it's as if I reach into that bin and without looking, I grab one of those signals. And all of those signals have slightly different behavior. Now, something called a probability density function, we'll use that to characterize the possible class of signals in the bin, so that if I pull one out, it is removed or selected on the basis of a so-called probability density function. And we will look at full random characterization for signals, but we're going to start with scalars. So we have a single value or a single sample, and we're going to look at how we can characterize that using the tools of probability and statistics. And we're assuming that you've had some exposure to probability and statistics, so this is somewhat of a review. So we'll define a random variable x, and that's a symbol that represents the unknown outcome of an experiment, like reaching into this big container and pulling out a number, for example. Now let's suppose we flip a coin. Well, in that case, we have two possibilities. We have a head or a tail, or we can think about that in terms of a binary value of either the random variable takes a 1, perhaps that corresponds to a head, or it takes on 0, corresponding to a tail. Now, if we have a fair coin, the probability that we get either of those results is 1/2. And we would say that the two outcomes of the experiment, x equals 1 or x equals 0, are equally likely. And of course, binary values are used often in communications because when we sample a signal, eventually we convert those samples down to a string of bits, 1s and 0s, that are associated with the binary representation for the sample. So we're going to transmit those, say, one at a time, and it's oftentimes equally likely that we'll get either a 1 or a 0 at any particular instant in time. And we can also have random variables that take on a continuum of values. For example, suppose that I have the performance of a bunch of different investment vehicles. Well, some of those are going to perform higher than others, and there's probably going to be some concentration about the middle, and the probability density function, which we'll denote as f of x, tells us a lot about the concentration or the range of possibilities that might occur when I select a particular investment vehicle. For example, if I have some interval between x1 and x2, the probability that a particular random experiment, say I randomly select an investment vehicle, the probability that its performance lies in this interval can be expressed as the area under the probability density function on that interval. So where f of x is fairly large, for a fixed interval, I have a higher probability of getting a value x there than I do say over here on the left, where f of x is very small. If I take the same sized interval and I look for the probability that I get a value that's in that interval, it's going to be quite a bit smaller. Now there's some common probability density functions that get used in signal processing, and one of them is a so-called uniform PDF. And in this case, the probability density function is a constant value between a and b. So this says that our random variable x is equally likely to occur anywhere between the endpoints a and b. The value of the probability density function is 1 over b minus a, because this has to integrate to 1. Now, one example of a uniform that comes up sometimes is, let's suppose we're looking at the phase of a sinusoid. So if I have x of n, the signal is equal to a cosine of omega naught n plus phi, we might, for example, assume that the phase is uniformly distributed between 0 and 2 pi. That would give us a sinusoid whose initial phase is random, and it's equally likely that the phase occurs anywhere in this particular interval. Another common probability density function is the Gaussian, and this is the so-called bell-shaped curve, and I've written out the expression. You've probably seen this before. It involves an exponential, and then we have the random variable x minus the mean squared divided by the variance in the exponential. So the mean is the center of concentration where mass is centered about, and sigma tells us how concentrated the PDF is. As sigma increases, the width of the PDF increases, and again, since this has to integrate to 1, if this gets wider, then the amplitudes get smaller. And there's a lot of different types of quantities that can be modeled by Gaussian. Perhaps even exam scores might be approximated by a Gaussian. In signals, we often have the amplitude of a signal might be represented by a Gaussian random variable. So the amplitude may have some mean value, and that mean could even be 0, and then there's some variability about the mean. So things like white noise, which we'll look at in more detail, often are assumed to have a Gaussian distribution for the amplitude of the signal. Now there are many other distributions that you can run into if you study probability and statistics. There's chi-squared random variables, Poisson, F, and distributed, and so on. And we're not going to look in much detail at many of these, because actually most of the time we are going to pursue a partial characterization of our signals, because the probability density function may be unknown ahead of time. I observe some data and no one tells me what the probability density function was that generated that signal. And secondly, I may not need or want all the details that are contained in the PDF. I can do a lot of signal processing without needing those details. And if I don't know the PDF ahead of time, then I may want to estimate certain quantities that tell me something about the uncertainty in the data, and that'll be a partial characterization. And the fewer quantities that I have to estimate, the easier this process will be. So often we work with summary statistics, and in signal processing, a lot of work is done just with mean and variance, and then their extensions to, beyond the scalar case, to multivariable quantities and signals, which we'll do in a following lecture. So the mean is, on average, if I repeat my experiment of reaching into the bin and selecting a number at random, on average, what value is observed? I repeat that experiment over and over. The variance is, on average, what is the squared distance of the values that I observe from the mean? So again, I can think about reaching into a container, pulling something out at random, and then I look at the value that I select and how far is that value from the mean, its squared distance. And then I repeat this experiment over and over and over, and on average, what do I get for squared distance from the mean? That tells us how concentrated the signal is about the mean. And amazingly, with these two quantities and their extensions to the signal or the vector case, we can do an amazing amount of signal processing. Now this brings about the notion of expectation. And the expectation is an operation which will denote by this E with the curly brackets and the quantity that we're taking the expectation of inside the brackets. And this is the result of averaging over an infinite number of experiments. So I keep reaching into this container and pulling out random numbers, and I average, and that's what expectation means. So the mean can be viewed as the average value of the random variable when I repeat an infinite number of experiments. And similarly, the variance, which we'll call sigma squared, is on average the squared distance from the mean. Now we can define expectation formally using the probability density function. In general, if I take the expectation of some function g of a random variable x, all that means is that I'm going to integrate g of x against the probability density function for x. And that's how I get my expectation. So if I think about the mean, which is the expected value of x, that's just the integral from minus infinity to infinity of x, f of x, dx. Now you see, to use these formal definitions and compute expectations, we need to know what the probability density function is ahead of time. We need to know f of x. And as we noted above, oftentimes we don't know the PDF, or we're trying to work without that level of detail. So in such cases, we'll use sample statistics, and for example, we'll take the mean. Suppose I collect n random variables that I repeat my experiment capital N times. Then I could say that the mean can be approximated as the average value. And of course, as n gets bigger, you'd expect that I should get a better and better approximation to the true value here, which we can think about the expectation being an average over an infinite number of experiments. And similarly, if I want to estimate the variance from my data, I can do that by averaging the squared distance from the mean over a series of experiments, capital N. And that's what we're going to end up doing oftentimes in real signal processing. We're going to estimate these sort of summary statistics involving quantities like a mean and a variance from the actual observed data and use that as part of our processing. And these tools, even working just with mean and variance, give us incredible power for separating signals from noise and exploiting different properties that are characterized by these types of statistics.